Okay, good morning, good afternoon, good evening class. This is Mr. Arocena, and on today's video, we're going to be talking about gravitational potential energy and how it pertains to escape velocity. Now, I've talked about gravitational potential energy before for normal Earth-based problems, and if you recall, to calculate gravitational potential energy for these problems, we would just take our force of gravity, so mass times g, and multiply it by how high the object is above the Earth's surface. Now, the Earth's surface, or I guess the planet's surface, is what we would call the zero energy level. And it makes a lot of sense because if our surface is here and we have an object, this object would have its potential gravitational energy would be zero. And then as we lifted the object above the ground, its potential energy would then be greater than zero. How big that is would be based on this height here. Now, for space-based problems, we actually kind of turn this problem on its head. We kind of reverse it. So for space-based problems, we actually take our zero energy level to be infinitely far from the Earth's surface. Now, part of the reason for this is because of how gravity is calculated and how the force of gravity is calculated in larger space-based problems. If you recall from previous lessons, our universal force of gravity was actually gm over r squared. And if we were to calculate the potential energy for really far away objects, potential energy would be basically the force of gravity gmm over r squared times the distance that they're separated. So this simplifies to this equation here. Okay. Now, the reason for the negative sign, some of you might have noticed this negative sign here. The reason for this negative sign is because the potential energy, when we take our energy level to be infinitely far from the Earth's surface, the potential energy is negative because that's kind of like the energy we have to give the object in order to drag it from infinity to somewhere closer to Earth, okay, or somewhere closer to the planet. So that's the reason for the negative sign here. Now, what this basically means is that if I want to, I guess, escape something's gravitational pull, I have to drag it far enough away that the force of gravity can be ignored. Okay. Now, in order to escape something's effective gravitational pull, we have to provide enough energy to equal the amount of work done by gravity. And what this means is this amount of work is basically how much work gravity did to drag the object from an infinite distance to itself. Okay, so let's see if I can illustrate this a little better. Okay, so as I mentioned, if I want to escape the effective gravitational pull of a body, I have to provide enough work to overcome, provide enough energy to overcome the work done by gravity. And I should make an addendum here: work done by gravity in attracting the object to itself. So you can sort of think of it as, if this is my planet and I have an object here, the planet is going to exert some force of gravity in this direction. And that force of gravity is going to be doing some work over this distance. So this is we'll call it r for argument's sake, distance. So the work done by gravity is going to be the force of gravity times r. Okay. Now, if I want to escape the object, if I want to escape gravity, then I need to provide enough energy to overcome the work, so this quantity here, that gravity did in dragging the object towards itself in the first place. And that's kind of why in the previous slide where our potential energy equation for gravity was negative, G-M-M over R. The negative sign kind of signifies that gravity did some work to drag the object to itself, so we have to supply the opposite amount of energy, I guess, to send it flying the other way. Okay? In reality, the negative sign is kind of pointless. It just shows us that this potential energy is kind of backwards what we would normally expect. Anyways, so in order to escape the force of gravity, I have to provide enough energy to overcome this quantity here, this potential energy that gravity did to drag it towards itself. Okay. Now, what does this mean for us? Well, by knowing how much energy an object has due to gravity dragging it towards itself, we can actually determine how much kinetic energy I need to overcome that. And from the kinetic energy needed, I can calculate the velocity that my object would need in order to escape the effect of gravitational pull of some object or some planet. So if we're trying to leave the Earth, we need to provide enough kinetic energy so that we can overcome the gravitational potential energy that is at the surface of the planet, or just for our case, surface of the Earth. What we're basically going to do is we're going to set the kinetic energy of our spacecraft has to equal the potential energy at the planet's surface. And this energy at the planet's surface is going to be the potential energy as calculated by this equation. Now, RE will refer to the planet's radius, and big M would refer to the planet's mass. And little m would basically be our spacecraft. That would be our spacecraft. Spacecraft. There we go. So by knowing this, we can then set the kinetic energy of our spacecraft must equal this potential energy that we are, the gravitational potential energy of the Earth, I guess, dragging something from infinity towards itself. Okay. All right, so as an example, we'll take this fictitious planet, and suppose a planet has this radius and this mass, and we want to calculate just what is the, I guess, we'll do two things first. What is the potential energy of a 1 kilogram object at the surface of this planet relative to space? That will allow us to calculate the potential energy using the G-M-M over R equation. And from this equation, we'll calculate what the escape velocity is in order to escape this planet's gravity. Okay, so first thing, we'll calculate the potential energy of a 1 kilogram object of this planet's surface. RE, there we go. And we'll just put our numbers. G, if you remember from earlier, is 6.67 times 10 to the negative 11, I think. Let me just quickly look that up. Yep, that's correct, negative 11. And we'll have units of meters cubed over kilogram seconds. The mass of the planet is going to be 3.98 times 10 to the 25 kilograms. The mass of the object is 1 kilogram. And we are all, dividing this by the radius of the planet, which is 1.74 times 10 to the 8 meters. Throwing that into our calculator, we get 6.67 to the negative 11 times 3.98 to the 25 times 1 divided by 1.74 to the 8. scientific notation, we got a potential energy of 1.53 to the 7 times 10 to the 7, and we'll put this in joules. There we go. So this is the amount of energy. Okay, so this is gravitational potential energy, but this is relative to infinity, relative to some infinite point in space. Okay. Now, we don't normally report that a 1 kilogram object has this much potential energy because it doesn't make much sense for Earth-based problems. But for space-based problems, this actually kind of makes a lot of sense. You can sort of think of it as this. If my planet is here, there's my planet, and my object, my 1 kilogram object, is somewhere in the middle of space, the force of gravity, as it's dragging this object this way, is doing work. So force of gravity does work to get object to the planet. And the sum of all the work that this force of gravity has done translates to this. Okay. So that's how much potential energy this object has gained, or how much work gravity has done on this object to get it from somewhere infinitely far to itself. Now, the escape velocity kind of plays on this, because if I have dragged this object from some infinitely far point in space to the planet, I would need to give the object enough energy to do the same. Okay, so in order to leave the planet, okay, we need enough kinetic energy to overcome the work, or the energy gravity, yes, well, we'll call it work energy that gravity did. So we need to provide enough kinetic energy. We need to provide this much kinetic energy in order to escape the planet. Okay. Now, interestingly enough, it doesn't actually matter what the mass of the object is, because kinetic energy of any object can be given by 1/2 mv squared. That's kinetic energy. And then we have to match the gravitational potential energy, or the work done by gravity, which is going to be gmm over r of the planet. And notice that the mass of the object will then cancel out, so we don't actually need the mass of the object. And to figure out how fast the object goes, we'll just solve this for v, so we get 2gmm over re divided by that. Or sorry, yeah, square root that. So we get the following then. So in order to escape this particular planet, we'll just calculate things out. Times 3.98 to the 25, all divided by 1.74 times 10 to the 8. So calculating all this, 2 times 6.67 to the negative 11 times 3.98 to the 25 divided by 1.74 to the 8 gives me this number, and then we'll square root that. So we get a velocity of 5.5 times 10 to the 3. So 5.5 times 10 to the 3 meters per second. So now for this particular planet, no matter how much mass the object has, as long as we can give it a velocity of about 5,500 meters per second, we can send it flying into space, Basically, we've given it enough energy that it can leave and not have to worry about gravity slowly pulling it back. There is enough velocity here going away from the planet that the force of gravity has minimal impact on it. Minimal pull. We basically drag the object far enough away that its momentum will not, the force of gravity will not be able to overcome the inertia momentum of the object as it's flying away. Okay. For our planet, we can do the same calculation for any planet, and we can sort of figure out, okay, how fast do I need to get the object going so that I can escape the gravitational pull of the planet that we're on. So that's kind of how we can determine escape velocity. We just basically take our kinetic energy and we set that equal to the gravitational potential energy as calculated by this equation. Okay. And again, this gravitational potential energy, so this potential energy gravity is relative to a point infinitely far away. It's not quite the same as how we calculated it before with force of gravity times height, or mg times h. Mg times h works great for Earth-based problems and where the distances are not incredibly large, but for space-based problems we have to use this equation here. It just makes a little bit more sense. So, with that said, you have a short assignment today. It'll be as follows. If you guys have any questions about this unit, you guys know how to contact me.